I am Jeroen and welcome to my lecture series on computer and network security. In this fifth video on symmetric ciphers, I will continue talking about the Advanced Encryption Standard or AES and provide you with more details on the different steps involved in each round of AES. So as a brief reminder, here you see how the first round of AES is performed. First, there's an initial transformation of the plain text block, which is 16 bytes large, using the add round key function. Then the first round consists of 4 functions, namely substitute bytes, shift rows, mix columns, and add round key. During each of the add round key functions, the round key is combined with the input block. In this video, I will explain the details of these 4 different functions, as well as how the original key is expanded into different round keys. Let's start with the first step, substitute bytes. The substitute byte step will, as the name implies, replace each byte with another uniquely determined random byte. How does it work? Well, the original byte in the input block, which consists of 4 by 4 bytes, is used to determine a unique position in the so-called S-box matrix. A byte consists of 8 bits, and the first 4 bits are used to determine the row, while the second 4 bits are used to determine the column. 4 bits give a number between 0 and 15, and the S-box has 16 rows and 16 columns, which can thus be uniquely identified by these 4-bit patterns. In the end, the S-box will thus assign each of the 256 unique 8-bit patterns to a different one. This allows the operation to be also reversed, as this mapping is unique. The output is another set of 16 bytes that are different from the original 16 bytes. And here you see the S-box that is used in AES. It is fixed and standardized, and the inverse S-box you see here. And if you look more carefully, you will see that they are indeed each other's inverse. For example, if you look at the element on the third row, so row number 2, and the 10th column, so column number 9, which maps the value 29 to A5. If we then go look at the value at position A5 in the inverse S-box, we see that it is indeed 29. So that means that they are each other's inverse. Second step is shift rows. Shift rows is quite straightforward. What it does is it takes the 16-byte 4x4 input matrix and just does a left circular shift of the bytes based on the row on which they are present. The first row is not shifted, so as you see, the first row of the input equals the first row of the output. The second row is shifted 1 position to the left, so S11 ends up at the first position, S12 goes from the third to the second position, S13 from the fourth to the third position, and S10 moves all the way from the left to the right, as it is a circular shift. Same thing is done on row 3, where the position is changed by 2, and row 4, where the shift is done by 3 positions, which corresponds to a single shift to the right. So the result of this shift rows operation is that all the bytes in each of the 4 columns will be spread across all of the columns. As you can see here, the bytes that end up in the first column come from all 4 original columns. Here you see an example for this input matrix, what would be the corresponding output. And you can check this at home to verify that it's correct. The third step in the process is mix columns. Mix columns will multiply our 4x4 input matrix with a constant 4x4 matrix. So the values in this matrix are fixed. They are small hexadecimal values. The reason they are small values is because this is easier to calculate, and thus the process is computationally more efficient. The output of this matrix multiplication will be the output of the mixed column step. Note that the multiplication is performed using Galois field theory, and specifically in the Galois field 2 to the 8. You can check the background material for more information on how to perform multiplication and summation using Galois fields. We can mathematically write down these multiplications as this matrix multiplications as follows. So the matrix multiplication, if you recall, the first element on the first row and first column is calculated by taking the first element of the first matrix on the first row and column, multiplying it by S0, 0, then taking the element on the first column, first row, second column, multiplying it by the element of the first column, but second row, adding multiplication of the third element on the first row with the third element of the first column, and finally adding the element on the fourth position of the first row and multiplying that with the element on the fourth position of the first column of the second matrix. And that's what you see here. And it's a basic matrix multiplication. To make sure everyone understands correctly how this multiplication of two matrices in the Galois field of 2 to the 8 works, I have an exercise for you. And the exercise is to calculate the output state of the first element of the first row and first column, so only this element, not the other ones, of the mixed columns transformation given this input state. So this S matrix corresponds to this input state. So I'll leave it up to you to do this exercise on your own. And obviously, for the mixed column step, we were able to choose the constant values in the matrix with which we multiply our input state. But for the inverse mixed column step, we cannot choose these values. They are determined by the inverse operation, because we need to go back from the output to the input. And the problem is that these inverse values are no longer small values. They are, as you can see, bigger values, which causes the decryption to actually be computationally more intensive than encryption. This is important to remember. The fourth step in a round of AES is the add round key step. This step is very straightforward. It basically takes the bitwise exclusive OR of our 16-byte input state with our 16-byte round key. So 16-byte state means 128 bits, so each of the 128 bits in our input is XORed with the corresponding bit in the round key, which is the same size. That results in our final output of the round. You can at home yourself verify this example to see whether or not it's correct. So these are the four rounds that are the four functions that are performed in each round of AES. And one by one, they will transform the 16-byte input matrix into a 16-byte output matrix. Obviously, in the final step of each round, the add round key, this matrix is combined with a 16-byte round key that is derived from the original key. The original key can be also 16 bytes, but can also be larger, up to 32 bytes. So here in this figure we assume the 16-byte original key, which is here represented as a 4x4 byte matrix. And this needs to be transformed into a 44-word, each word consisting of 4 bytes, round key set. Each subsequent 4 words comprise a single round key. So word 0 to word 3 is the first round key, while word 40 to word 43 is the last round key. So round key number 11. The original key is directly transformed into the first round key. So bytes K0 up to K3 form word 0, and K12 up to K15 form word 3. Then these initial 4 words are combined using an XOR operation and a function G into 4 new words. And here you see what the function G looks like. So the function G starts with a word of 4 bytes. So this word consists of bytes 0, 1, 2, and 3. And then it performs a left circular shift of a single byte. That means that byte 1 goes to position 0, byte 2 goes to position 1, byte 3 goes to position 2, finally byte 0 goes to the right to position 3. The next step, this function G performs a substitution using the same box, and the same technique as sub-byte steps of the AES algorithm. Finally, the word, so the 4-byte word, is XORed with a constant. This constant is different in every round, and here you see the example when we have 10 rounds of AES, which is the case with a 16-byte key. And in the first round, the value of this constant is basically 0, 1 in hexadecimal followed by 3 0 bytes. So that means first 8 zeros, 7 more zeros, a 1, followed by 3 times 8 zeros. So this is how the original key, in this case of 16 bytes, is expanded into 11 round keys, each consisting of 4-byte words. And this also concludes our video on AES.